You think mega-tsunamis come from earthquakes? Most people do. The ground shakes, the ocean rises, waves hit the coast. Simple story. Except it is not. September 2023. Seismologists across the planet pick up a signal. Not an earthquake, something else. A hum. One frequency. 90 seconds apart. 9 straight days. Nobody had seen this before. The instruments worked fine. The signal traveled through Earth's crust from Greenland. 68 scientists from 41 institutions spent a year solving it. What they found changes everything we thought we knew about the strangest waves on the planet. A mountain collapsed, 1.2 kilometers high, Dixon Fjord, eastern Greenland. 25 million cubic meters of rock and ice, enough to fill 10,000 Olympic pools. The peak hit water and threw a splash 200 meters into the air. The wave reached 110 meters tall and stretched 10 kilometers across the fjord. Within minutes, it dropped to 7 meters. Then it did something nobody predicted. It kept going, back and forth. A sea water sloshing in a bathtub. For 9 days, the wave rose and fell every 90 seconds. It pushed on the seafloor like a piston, created seismic energy that rang through the planet. Scientists call it the Greenland Mega-Tsunami of 2023. The mechanism is glacier thinning. Climate change melts the ice at the base. The glacier that once held up the mountain face is gone. The rock has no support. 30 meters of ice thickness lost over decades. The mountain sits on unstable ground. Gravity takes over. September 22nd, 2023, around 1:57 UTC. The entire southwest face lets go. Researchers used satellite imagery, seismometers, infrasound data, field measurements, and computer models to reconstruct what happened. The Danish military sailed into the fjord days after. They photographed the collapsed mountain face, fresh scars on both sides. 70 kilometers away at Ella Island, waves 4 meters high destroyed a research base, $200,000 in damage, archaeological sites across the fjord system wiped out. No people died because no cruise ships were there that day. If one had been, the wave would have killed everyone aboard. Stephen Hicks from University College London saw the seismic data first. He thought his instruments were broken. An earthquake produces a rich mix of frequencies. This was one pure tone, a monotonous hum. It baffled him. Christian Svenevig from the Geological Survey of Denmark and Greenland led the investigation. When they started, nobody had any idea what caused the signal. They only knew it connected to a landslide. The team built mathematical models of the fjord at very high resolution, width and depth mapped precisely. They recreated how the mass of water moved. The rhythm matched the seismic signal exactly. Alice Gabriel from UC San Diego's Scripps Institution ran supercomputer simulations. The challenge was modeling a tsunami that sloshes for over a week. The simulations matched the real wave height and the oscillation pattern. Before this, scientists had no idea a seiche could last 9 days. Svenevig said finding this was like discovering a new color in a rainbow. Eastern Greenland had never experienced a landslide and tsunami like this before. The Arctic is warming 4 times faster than the rest of the world. Greenland's ice cap loses 30 million tons of ice per hour. New areas are coming online for these climate events. In June 2017, a tsunami in northwest Greenland killed 4 people and destroyed houses. The threat extends beyond Greenland. Similar fjords exist in Alaska, parts of Canada, and Norway. This is not a Greenland problem. This is a global shift. If you value documented geological and climate history like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. Also, this script is researched and factual, using sources from the journal Science published September 12, 2024, confirmed by 68 researchers from 40 institutions across 15 countries, with additional verification from Nature Communications, Earth and Environment, and the European Geosciences Union. Peer-reviewed work that took nearly a year of international collaboration to complete. Now back to the information. August 2025. Alaska. Another one. Pedersen Glacier in a remote fjord near Juneau. A massive landslide. The mountainside detached, slid into deep ocean water. The wave that followed reached between 470 and 500 meters high. Taller than every building in New York City except One World Trade Center. Scientists flew in by helicopter. They measured the run-up height using GPS and altimeter readings. The wave created a seiche, water sloshing back and forth for days. 3 kayakers camping on an island at the fjord mouth had their gear swept away. They made it out alive. The U.S. Geological Survey warns the landslide scar remains unstable. Continued rockfall and smaller landslides are expected. The area stays hazardous. Future local tsunamis are likely. These are not isolated incidents. Go back to 1958, July 9th, Lituya Bay, Alaska, 10:15 p.m., still daylight, clear weather. Magnitude 7.8 earthquake on the Fairweather Fault. A mountainside, fractured, 40 million cubic yards of rock, that is 90 million tons, 8 million dump truckloads. The rock fell from a height of 2,000 feet. It slammed into Gilbert Inlet at the head of Lituya Bay. What happened next defied everything scientists thought possible. The wave reached 524 meters, 1,720 feet, 8 times higher than any landslide-generated wave ever recorded. The trim line is still visible from space 67 years later. Bill and Vivian Swanson were anchored in their boat in Anchorage Cove. Bill later reported something impossible. He saw Lituya Glacier rise into the air. The glacier was hidden behind a point. You cannot see it from Anchorage Cove, but that night he watched it lift several hundred feet. It was jumping and shaking. The glacier was in sight. Scientists later confirmed the earthquake caused massive ground displacement. The rock impact created a cavity in the inlet floor. Similar to an asteroid strike, it launched water upward and outward. The initial wave was 1,500 meters high. A curtain of ejected material pushed water in all directions. Within 2.5 minutes, a 4.5 kilometer high wave formed, then subsided as debris fell back. 10 minutes after impact, a 1.5 kilometer high ring-shaped wave began sweeping outward. The wave destroyed 2 fishing boats. A husband and wife died. One boat was lifted over a forested spit on the wave crest. The captain looked down at trees below him. The wave stripped vegetation up to an elevation of 700 feet around most of the bay. On the ridge opposite the slide, the splash reached 1,720 feet. Scientists call this the maximum run-up height. The evidence remains. Light-colored vegetation shows where mature forest was ripped away. Trees, 4 feet in diameter, sheared at the base. Bark stripped. The damage extends 2 square miles. The scar is permanent. Don Miller from the U.S. Geological Survey flew over 12 hours after the earthquake. He interviewed survivors. He measured trim lines on the hills. He found evidence of previous giant waves, 1854, 1874, 1936. The 1899 earthquake triggered a wave that destroyed a native village and drowned 5 people. Lituya Bay produces mega-tsunamis roughly every 100 years. Here's where it gets strange. Scientists initially could not explain the wave height. Landslides are inefficient at generating tsunamis. The energy transfer from rock to water is only 4%. No known landslide had ever produced a wave approaching this magnitude. Los Alamos National Laboratory ran mathematical models. Charles Mader and collaborators in 1999 and 2002 used hydrocode simulations. They confirmed sufficient water volume and sediment depth existed to account for the giant wave. A 2010 study by Stephen Ward and Simon Day from UC Santa Cruz proposed a dual slide mechanism. The rockfall triggered the release of sediment trapped by Lituya Glacier, 5 to 10 times the volume of the initial rockfall. Glacial deposits on the fjord floor failed in a secondary submarine slide. This explained the massive infill found on the bay floor. The combination created the unprecedented wave height. Laboratory experiments at ETH Zurich reproduced the mechanics. A pneumatic landslide generator launched granular material at 110 meters per second. It created a large air cavity and a non-linear wave 160 meters high. The wave ran up to 530 meters elevation. The measurements matched the real event. The geometry matters. Lituya Bay is a T-shaped fjord, 7 miles long, 2 miles wide, maximum depth 722 feet. The narrow entrance has a depth of only 33 feet. The 2 arms at the head, Gilbert and Crayon Inlets, sit on the Fairweather Fault. A tectonic trench. The confined space amplified the wave. Water could not disperse. The U-shaped seafloor channeled energy. French explorer Jean-François de Galaup-Lapérouse visited in 1786. He noted a strange line in the forest, trees cut cleanly as with a razor blade. He sent 3 boats to measure water depth near the entrance. The weather was calm. 2 boats capsized, roiling tidal currents amplified by the fjord's narrow shape. 26 men drowned. The island in the bay was named Cenotaph, Greek for empty tomb. Lapérouse saw evidence of past mega-tsunamis 239 years ago. Current science shows these events cluster in deglaciated regions. Alaska has experienced multiple large landslide tsunamis in recent decades. 2014, Mount Lapérouse, 68 million ton landslide, 1.5 times the size of the Lituya Bay rock slide. It ran out onto a glacier, no water impact, no tsunami. June 2016, Lamplugh Glacier, over 100 million tons, also onto a glacier. 2015, Tanfjord, Portugal, an inlet of Icy Bay, 180 million tons, the largest non-volcanic landslide ever documented in North America. Part landed on Tyndall Glacier. Enough hit water to generate a significant tsunami. The pattern is clear. Glaciers retreat. Slopes lose support. Mountains collapse. When they hit water, mega-tsunamis form. Now go back 66 million years. The Chicxulub impact, an asteroid 14 kilometers in diameter, struck shallow water near the Yucatan Peninsula. It was moving at 12 kilometers per second, 27,000 miles per hour. The impact energy was 72 teratons of TNT, 3 times 10 to the 23rd joules, 5 billion Hiroshima bombs. The asteroid excavated a crater 100 kilometers wide and 30 kilometers deep. Within seconds, bedrock and sediment blasted into the upper atmosphere. 2.5 minutes after impact, a curtain of ejected material pushed water outward. It formed a 4.5 kilometer high wave, nearly 3 miles tall, the tallest wave ever modeled. As ejecta fell back to Earth, the wave subsided 10 minutes after impact. 220 kilometers from the point of strike, a 1.5 kilometer high tsunami wave began propagating outward, ring-shaped, moving in all directions. Molly Range, from the University of Michigan, led a team that modeled the Chicxulub tsunami. Published in AGU Advances in October 2022, they used 2 stages. First, a hydrocode called iSail simulated the chaotic first 10 minutes, crater formation, initial wave generation, then 2 tsunami propagation models, a MOM6 and MOST I. Tracked the wave for 48 hours across ancient ocean basins. The models used a paleogeographic map. Continental positions 66 million years ago were different. The Central American Seaway connected the Gulf of Mexico and Pacific Ocean. No land bridge existed between North and South America. The tsunami entered the Pacific freely. 1 hour after impact, the wave spread outside the Gulf of Mexico into the North Atlantic. 4 hours later, it passed through the Central American Seaway into the Pacific. 24 hours after impact, waves crossed most of the Pacific from the east, most of the Atlantic from the west, and entered the Indian Ocean from both sides. Open ocean wave heights in the Gulf of Mexico exceeded 100 meters. Wave heights reached more than 10 meters as the tsunami approached North Atlantic coastal regions and parts of South America's Pacific coast. The waves scoured the seafloor. Underwater current speeds exceeded 20 centimeters per second, strong enough to erode fine-grained sediments. Compare that to less than 1 centimeter per second for earthquake-generated tsunamis. The Chicxulub tsunami was 30,000 times more energetic than the 2004 Indian Ocean tsunami. The waves disturbed sediments in ocean basins halfway around the globe. They left either gaps in the sedimentary record or jumbles of older sediment. Researchers examined geological records at over 100 sites worldwide. The evidence matched the model predictions. In Louisiana, beneath what is now land, scientists found fossilized megaripples, average wavelengths of 600 meters, average wave heights of 16 meters, the largest ripples ever documented. The Chicxulub impact produced a truly global mega-tsunami. The initial energy was unmatched in recorded history. Now consider volcanoes. December the 22nd, 2018, Anak Krakatau, Sunda Strait, Indonesia. The volcano had been erupting since June. Strombolian activity, lava flows, ash plumes up to 5 kilometers high. The southwest flank was unstable. The volcano sat on the rim of the 1883 Krakatau caldera. A 200 to 300 meter deep basin, no buttressing support on the southwest side. The flank had grown steep. Researchers in 2012 predicted a collapse could happen. They modeled the potential tsunami. They calculated an initial wave height of 43 meters. They estimated the wave would reach the western coast of Java and southeastern coast of Sumatra at approximately 2 to 3 meters height. 10 years later, it happened. December the 22nd, around 1:57 UTC, the subaerial cone collapsed. Approximately 64 hectares slid into the ocean. The volcano's height dropped from 338 meters to 110 meters, between 0.22 and 0.30 cubic kilometers of material. The volume is debated. Some estimates go as low as 0.175 cubic kilometers, others as high as 0.28 cubic kilometers. The collapse generated a tsunami. Waves struck the coastlines of southeastern Sumatra and western Java between 1427 and 1500 UTC, 2127 to 2200 local time. No warning. No earthquake, ground shaking, no alert system. The tsunami arrived during evening hours, Christmas and New Year holiday season. Tourist areas packed. The wave reached at least 2 meters height in Kurita, more than 5 meters in Tanjung Lesung. Later surveys revealed 13.4 meters in some locations. Near-field run-up reached up to 85 meters close to the volcano. 437 people died, tens of thousands injured. The deadliest volcanic tsunami since the 1883 Krakatau eruption and the 1888 Ritter Island collapse. Both killed over 35,000 people. For the first time in over a century, scientists had a major volcanically generated tsunami with modern instrumentation and data. The mechanism was an en masse failure, not a gradual piecemeal collapse. The entire southwest flank let go at once. Satellite data from Sentinel-1A confirmed this. Images from December 10th showed the intact cone. December 24th showed massive modification. December 28th showed the final state. The flank had failed in a single event. This matters because the tsunami characteristics depend on failure speed and volume. A slow retrogressive failure generates smaller waves. A rapid en masse collapse creates much larger waves. Seismic stations recorded unusual signals. No clear body wave arrivals, typical of tectonic earthquakes. The automated detection system could not recognize the event. This caused the failure to issue tsunami warnings. The mechanism was different. Researchers had to develop new detection methods using seismic amplitude distributions. Stephen Grilly and collaborators from the University of Rhode Island modeled the tsunami, published in Marine Geology in July 2021. They tested different landslide rheologies and volumes. The 0.224 cubic kilometer collapse with specific material properties best reproduced the observed near-field and far-field tsunami flow depths, run-up heights, tide gauge records, and eyewitness reports. Current numerical models can accurately forecast tsunamis from volcanic flank collapses. The problem is warning systems. Without precursory signals and with short travel times, coastal populations have no time to evacuate. The pattern extends back through time. Storegga Slide, Norwegian Sea, approximately 8,150 years ago, 6,225 to 6,170 BCE, based on carbon dating of plant material. 3 submarine landslides. The largest known exposed submarine landslides in the world, 290 kilometers of coastal shelf, total volume 3,500 cubic kilometers, 840 cubic miles. The debris field extended from 100 kilometers off Norway's Moor coast into the abyssal plain, 1,600 kilometers into the Norwegian Sea, an area of 95,000 square kilometers. The scar is visible on the seafloor today, identified in 1983. The mechanism is debated. Most scientists believe a series of undersea earthquakes weakened the head wall of the continental shelf. Another hypothesis involves methane clathrate, gas hydrates trapped in seafloor sediments. An earthquake could trigger catastrophic expansion. 1 cubic meter of clathrate expands to 164 cubic meters of methane. The rapid release destabilizes sediment. A third theory involves glacial isostatic adjustment. The weight of glaciers during the last ice age depressed the crust. As glaciers melted, the crust rebounded. This created stress in sediment layers. Sediment overburden from rapid post-glacial deposition added weight. The combination triggered failure. New research published in Communications, Earth and Environment in February 2023 revised the understanding. The Storegga slide was smaller than previously thought. Much of the northern slide scar was from an earlier event. The Nyega slide, approximately 20,000 years ago at the end of the last glacial maximum. This removed over 35 meters of sediment previously attributed to Storegga. Large slope failures at the mid-Norwegian margin occur more frequently than believed. The tsunami hazard is higher. The Storegga tsunami was massive. Wave heights reached 20 to 25 meters along the Shetland Islands coast, 10 to 12 meters along Norway, 5 meters along eastern Scotland. The waves traveled up to 80 kilometers inland, 6 meters above normal tide levels. The sea level was 14 meters lower then than today. Tsunami sediment appears in Scotland's Montrose Basin and Firth of Forth, 29 kilometers inland, 4 meters above current tide levels. Evidence exists in Iceland, Norway, the Faroe Islands. The tsunami struck Doggerland, the land bridge connecting Great Britain to Denmark and the Netherlands. Mesolithic humans lived there. Lagoons, marshes, mudflats, beaches, rich hunting and fishing grounds. The tsunami may have accelerated the final inundation of Doggerland. Some scientists estimate up to a quarter of Britain's Mesolithic population died. Archaeological evidence is scarce. The underwater investigation is difficult, but cores taken from the former Doggerland region show tsunami deposits. The Storegga tsunami was a civilization-altering event. Here is the critical difference. Earthquake tsunamis and landslide tsunamis behave differently. Earthquake tsunamis exhibit shallow waves in deep ocean. They increase dramatically in height when approaching land. Maximum run-up around 30 meters for the most powerful earthquakes. Landslide mega-tsunamis can have initial wave heights in the hundreds of meters. The water is splashed upward and outward by displacement. The mechanism is impact, not tectonic uplift. If the landslide or impact occurs in a confined body of water, the wave cannot disperse. Lituya Bay. Dixon Fjord, Vajont Dam in Italy. The waves become trapped and amplified. October 9th, 1963. Vaillant Dam, a 250 cubic kilometer landslide from Montauk. The slide overtopped the dam with a 250-meter surge. Nearly 2,000 people died in the villages of Longarone, Parago, Rivalta, Villanova, and Faye. This was a human-caused mega-tsunami. Dam construction destabilized the valley sides. Now add glacier calving. Ekip-Sirmia, West Greenland, an outlet glacier of the Greenland ice sheet. The ice cliff is 200 meters high. The fjord is 125 meters deep. Calving events regularly produce tsunami-like waves. Field measurements show wave amplitudes up to 50 meters near the calving front, 3.3 meters at a tide gauge, 2,000 meters away. Laboratory experiments and computer models using the material point method reproduce these waves. The MPM technique, used for realistic snow in movies like Frozen, accurately simulates ice fracture mechanics, fluid dynamics, and the interaction between ice and water. Gravity and buoyancy together control the calving mechanism. If water level is low, the iceberg breaks from the top. If water level is high, the iceberg is longer and breaks from the bottom before floating to the surface. Gravity-dominated falls produce waves roughly 10 times larger than buoyancy-dominated rises. A 200-meter gravity fall into 125 meters of water can generate waves 20 meters high. The impact extends beyond immediate wave hazard. Internal tsunamis form underwater. When large icebergs calve, they displace water rapidly. The displaced water creates waves that propagate through stratified ocean layers. These internal waves break and cause vigorous mixing. Research published in Science Advances shows that glacier calving in Antarctica triggers internal tsunamis that drive mixing comparable to winds, and much more important than tides in regional shelf mixing. Bergen Bay, Antarctic Peninsula, January and February 2020. A large calving event. The internal tsunami mixed the water column throughout the fjord. Turbulent kinetic energy dissipation reached 0.134 watts per square meter, averaged over 61 hours. Or 0.307 watts per square meter, using the interval from calving to the second measurement. This mixing affects ocean stratification, marine ecosystems, nutrient distribution, and ice melt rates. Internal tsunamis from calving occur frequently. Thousands of glaciers calving around Antarctica continuously generate these waves. This mechanism was not factored into climate models. The discovery changes understanding of Antarctic ocean mixing, ecosystem function, and sea level rise projections. The frequency is accelerating. Climate change drives glacier retreat. As glaciers thin and recede, slopes become unstable. Mountains lose buttressing support. The probability of large landslides increases. Alaska has seen a spike in tsunami-generating landslides since the 1990s. Bethany Higman, a geologist studying Alaska's fjords, notes that going back to the 1990s, you find none. Then suddenly, multiple events in the 2000s, 2010s, and 2020s. The pattern is undeniable. Tracy Arm in August 2025. Kenai Fjords in 2024 producing a 55-foot wave. Ton Fjord in 2015. The 2025 Alaska Mega-Tsunami reached 500 meters. These are not 100-year events anymore. They are happening every few years. Barry Arm is the warning. A slow-moving landslide near Whittier, Alaska. Volume of nearly 18,000 cubic feet. Spanning 1.5 miles, as high as 3,000 feet. The U.S. Geological Survey discovered it in 2020. They now use ground-based radar, seismometers, cameras, and infrasound arrays to monitor it continuously. It is the only monitored unstable slope in Alaska. If Barry Arm fails, it will generate a massive tsunami in Prince William Sound. The question is not if, but when. Scientists estimate months to years, maybe decades. The slope moves slowly. But once it accelerates, failure could happen in seconds. A tsunami in Prince William Sound would threaten Whittier, Valdez, and other coastal communities. Cruise ships frequent the area. Tour boats bring thousands of visitors each summer. A warning system is essential. But most Alaskan landslide sites remain unmonitored. The Tracy Arm collapse happened without warning. The kayakers had no idea landslides were even a risk. Everyone told them to avoid calving glaciers. Nobody mentioned collapsing mountains. The cruise ship industry faces new risks. Alaska's Inside Passage attracts over 1 million cruise passengers per year. Glacier viewing is a primary attraction. Ships navigate narrow fjords to get close to tidewater glaciers. The same confined channels that create spectacular views also trap tsunami energy. A 15-foot wave from glacier calving is manageable. Captains know to slow down and point the bow into the wave. But a 100-foot wave from a landslide in a narrow fjord allows no escape. The ship cannot turn around in time. The wave hits broadside. Devastating. After the Tracy Arm event, tour operators are reassessing routes. Some areas may become too dangerous. But tourism pressure drives ships into risky locations. Passengers pay for close glacier encounters. Companies deliver. The safety margin shrinks. The mechanisms compound. Greenland loses ice. Mountains destabilize. Landslides increase. Each landslide triggers tsunamis. The tsunamis cause internal ocean mixing. The mixing brings warm water to glacier bases. Glaciers melt faster. The cycle accelerates. Iceland, Norway, Alaska, Greenland, Antarctica, Patagonia. Anywhere with marine terminating glaciers and steep topography faces increased risk. The 2023 Greenland event shows mega-tsunamis can occur in previously stable regions. Eastern Greenland had no recorded landslide tsunamis before September 2023. Now it is one of the largest documented seiches in history. The Arctic is entering uncharted territory. Return to fundamentals. What makes mega-tsunamis strange is the mismatch between cause and effect. A mountain collapses. This happens constantly. Mountains erode. Rock falls. Gravity pulls. But when that rock hits water in the right geometry, at the right speed, with the right volume, the wave exceeds all proportion. Lituya Bay, 524 meters from 90 million tons of rock. The energy transfer seems impossible. 4% efficiency should not generate waves over half a kilometer high. Yet it did. The dual slide mechanism explains some of it. The submarine sediment failure added energy. But even combined, the numbers barely work. The confined geometry amplified the wave. The T-shaped fjord with shallow entrance and deep basin. The wave had nowhere to go. It built up. It ran up the opposite slope. The splash reached heights no earthquake tsunami could achieve. The mechanism is impact-focused displacement in confined spaces. Chicxulub shows the upper limit, 4.5 kilometers, nearly 3 miles high. The initial splash, driven by an asteroid impact at 12 kilometers per second, 72 teratons of energy, that wave exists at the boundary between tsunami and something else entirely, a hydrodynamic phenomenon that reshapes coastlines on a planetary scale. The mega ripples in Louisiana are the fingerprint, 600-meter wavelengths, 16-meter heights, frozen in rock. 66 million years later, we can measure the violence. Anak Krakatau shows volcanic instability, a cone built in 90 years. From submarine volcano to 338 meters above sea level, rapid growth, weak foundation, unstable volcanic deposits stacked steeply. The southwest flank sitting on a caldera rim with no support. Climate change is not the driver here. Volcanic activity is, but the mechanism is the same. Gravity, instability, sudden failure, impact, tsunami, 437 dead. The volcano was monitored. The eruption was ongoing. Seismometers recorded activity, yet the collapse generated no standard earthquake signature. The warning systems missed it. The tsunami arrived without alert. This is the challenge. Mega-tsunamis from landslides and collapses do not follow earthquake rules. Detection requires different methods. Recognition of precursors is harder. Warning times are shorter. Storegga reveals prehistoric scale. 3,500 cubic kilometers, 8,400 cubic miles, an entire section of continental shelf, gone. The scar is 95,000 square kilometers, bigger than Portugal. The debris traveled 1,600 kilometers. Across the abyssal plain into deep ocean, the tsunami crossed the North Atlantic. It inundated coastlines from Norway to Scotland. It may have drowned a quarter of Mesolithic Britain. This was not a local event. This was a regional catastrophe. And it happened because sediment sat unstably on a shelf. Post-glacial rebound, methane expansion, earthquake trigger. The exact cause is still debated, but the result is clear. When enough material fails underwater, the resulting tsunami threatens entire coastlines. The geometry of catastrophe is precise. For a landslide tsunami, the key factors are volume, density, speed, water depth, entry angle, and confinement. A small, fast landslide into shallow water in a narrow fjord generates a higher wave than a large, slow landslide into deep open ocean. Lituya Bay had optimal catastrophic conditions: steep rock face, high drop, direct impact into confined inlet, dual slide mechanism, shallow exit to trap energy. The wave had no choice but to go up. Greenland's Dixon Fjord in 2023 had similar geometry. Narrow fjord. Mountain collapsed from 1.2 kilometers height. 25 million cubic meters. The wave reached 110 meters and sloshed for 9 days. The confined space sustained the siege. In open ocean, the energy would have dispersed in hours. The geometry trapped and amplified. Anak Krakatau sat in the Sunda Strait. Not a confined fjord, open water, yet the tsunami killed over 400. Why? The volume was large enough, 0.2 to 0.3 cubic kilometers. The collapse was rapid, en masse failure. And the wave traveled short distances to heavily populated coastlines. Java and Sumatra are densely populated. Coastal communities directly in the path. Travel time from collapse to impact was 30 minutes or less. No warning. Nighttime, holiday season, the combination was lethal. Even a moderate-sized collapse tsunami can cause mass casualties if it strikes the right place at the right time. Chicxulub had no geometry limitations, open ocean, global propagation. The Central American Seaway allowed the wave to enter the Pacific. No land bridge to block it. Ancient ocean basins were configured differently. The tsunami reached every coastline. The energy was so vast that even attenuation over thousands of kilometers left devastating waves. 10 meters approaching North Atlantic coasts, seafloor scouring halfway around the globe. This is the ultimate mega-tsunami, caused by the ultimate impact, an asteroid strike. Now the pattern becomes clear. Mega-tsunamis happen when massive displacement occurs rapidly in or near water. The displacement can be rock, ice, or asteroid. The mechanism is impact, not tectonic uplift. The resulting waves can be an order of magnitude larger than earthquake tsunamis. The confinement geometry determines amplification. The travel distance determines attenuation. The coastal population determines casualties. And the warning time determines survival. Earthquake tsunamis give minutes to hours of warning. Seismometers detect the quake. Tsunami buoys measure the wave. Alerts go out. People evacuate. Landslide tsunamis give seconds to minutes. No earthquake precursor. No standard seismic signature. The first warning is often the wave itself. If you are in the impact zone, you are already dead. If you are nearby and the wave is confined, you have seconds. If you are distant in open ocean, you might have minutes. The geometry of catastrophe is also the geometry of survival. Climate change is making this worse. Glacier retreat destabilizes slopes. More landslides, more tsunamis. The Arctic is warming 4 times faster than the global average. Greenland loses 30 million tons per hour. Alaska's glaciers recede kilometers per decade. Antarctic ice shelves thin and collapse. Each retreat removes support from adjacent rock. Each thinning reduces buttressing. The probability of failure increases. The 1990s had almost no large landslide tsunamis in Alaska. The 2020s have had multiple. The frequency is rising. The magnitude is rising. The August 2025 Alaska event was 500 meters, half a kilometer, in a region with increasing cruise ship traffic. The risk is compounding. The Greenland event shows this is global. Eastern Greenland was considered stable. No history of major landslides, no significant tsunami risk. September 2023 changed that assessment. If Eastern Greenland is vulnerable, everywhere is vulnerable. Norway's Storegga region had 3 massive failures in prehistory. Could it happen again? The Ormen Lange gas field development assessed the risk. The conclusion was that recurrence requires another glaciation. Sediment must accumulate unstably on the shelf. This takes tens of thousands of years. The risk was deemed negligible for current operations. But that was before climate change altered the equation. Rapid ice loss, isostatic rebound acceleration, methane destabilization from warming waters. The old models may no longer apply. The science is clear. Mega-tsunamis are not rare prehistoric events. They are happening now. They are increasing in frequency. They are driven by climate change in polar regions and by volcanic instability in equatorial regions. The mechanisms are well understood. Impact displacement, rapid failure, confined geometry. The waves can exceed 500 meters. The casualties can number in thousands. The economic damage runs into billions, and the warning systems are inadequate. We can detect earthquakes globally in seconds. We struggle to detect landslides locally in minutes. The gap is deadly. The solutions exist, but are incomplete. Ground-based monitoring, radar, seismometers, infrasound arrays, cameras, real-time analysis, automated alerts. These work for known threats like Barry Arm, but Alaska has thousands of potentially unstable slopes. Greenland has thousands more. Norway, Iceland, Patagonia, Antarctica. We cannot monitor everything. The alternative is ocean-based systems, pressure sensors on the seafloor near potential source regions, telemetry to land, detect the wave as it forms, issue warnings immediately. But deployment is expensive, maintenance is difficult. Power and communication require undersea cables. The cost runs into hundreds of millions per system. Few governments prioritize this investment. The Tracy Arm event happened unmonitored. The kayakers survived by luck. The next group might not. The cruise industry must adapt. Route planning that accounts for landslide tsunami risk. Real-time monitoring of unstable slopes along shipping lanes. Communication systems to alert ships immediately. Crew training for tsunami response in confined fjords. Passenger briefings on evacuation procedures. Some of this is happening. Much is not. The pressure to deliver spectacular glacier views competes with safety margins. Companies that avoid risky areas lose customers to companies that do not. The market incentivizes risk. Regulation must counteract this. Alaska has begun restricting access to some areas. More restrictions are coming. The question is whether they come before or after a major disaster. For coastal communities, the message is stark. If you live near steep mountains and water, you're in a potential mega-tsunami zone. Earthquake building codes will not save you. Seismic sensors will not give advance warning. The wave will arrive with little or no precursor. Your survival depends on elevation and distance. If you can see the water can reach you. If you can reach high ground in under 5 minutes, you might survive. If not, you will not. This is not hyperbole. This is the documented reality from Lituya Bay, Anak Krakatau, Greenland, and Norway. The geological record confirms this. Trim lines on hills. Boulder deposits far inland. Sediment layers disrupted. Mega ripples on ancient seafloors. The evidence is everywhere once you know what to look for. Mega-tsunamis have reshaped coastlines throughout Earth's history. They will continue to do so. The only question is frequency and location. Climate change is increasing the frequency. Tectonic and volcanic processes determine some locations, but the Arctic and subarctic regions are now in the crosshairs. Every year brings more glacial retreat. Every retreat increases landslide probability. Every landslide risks a mega-tsunami. Here is the final piece. The Greenland Siege. 9 days, 90-second rhythm, 1 frequency. Detected globally. This was unprecedented. Nobody predicted a seiche could last that long. The discovery changes understanding of how energy propagates through Earth's crust. Seismic networks detected a signal they could not explain. The signal did not match earthquakes, explosions, or any known source. It took 68 scientists from 41 institutions in 15 countries nearly a year to solve it. The answer was a wave trapped in a fjord sloshing back and forth, creating rhythmic pressure on the seafloor, generating continuous seismic energy. The mechanism had never been observed before at this scale and duration. It expands the catalog of possible seismic sources. It shows that mega-tsunamis can create global signals distinct from earthquakes. This has implications for monitoring. If future landslide tsunamis generate similar signals, seismometers worldwide could detect them with proper algorithms. Automated systems could identify these events within minutes. The warning window remains short, but minutes are better than nothing. The soil core from the Dixon Fjord seafloor will show the impact. Sediment disturbed by the seiche, layers mixed, transported material. When scientists drill and analyze the core, they will see the fingerprint of the 2023 event. Decades from now, researchers will study this core to understand how a mega-tsunami modifies fjord sediments. Just as we study ancient cores to understand past events, the cycle continues. Catastrophe, investigation, understanding, prediction, mitigation, repeat. Each event teaches us, each death is a data point, each survivor is a lesson. The goal is to move from reactive to proactive, to predict before it happens, to warn before the wave arrives, to evacuate before impact. We are not there yet, but we are closer than we were. The strange truth about mega-tsunamis is this: they are not strange at all. They follow physics, mass displacement, gravity, fluid dynamics, energy transfer, wave propagation. The math is well established. The mystery is not how they happen, but when and where. The triggers are varied. Earthquakes, volcanoes, glacier retreat, asteroid impacts, methane release, sediment failure. Human activity. The common thread is instability. Something sits at the edge of failure. Gravity pulls. Support gives way. Material falls or collapses or impacts. Water displaces. Waves form. If the geometry amplifies, mega-tsunami results. If the geometry disperses, ordinary waves result. The difference is location and scale. Lituya Bay shows the local extreme, confined fjord. Steep drop, dual slide. 524 meters, 9 deaths, 2 square miles destroyed. But the impact is local. The wave does not leave the bay. The outside world barely notices. Chicxulub shows the global extreme. Asteroid impact, initial wave 4.5 kilometers. Open ocean propagation, global seafloor scouring, sedimentary record disrupted on every continent. Mass extinction event, 3/4 of all species dead. The mega-tsunami is one part of a planetary catastrophe. These are the endpoints. Most events fall between. Anak Krakatau is typical of volcanic collapses. 0.2 to 0.3 cubic kilometers, waves up to 85 meters near field, 10 meters at coastlines, 437 dead. Regional disaster, not global, not localized. Storegga represents large submarine failures, thousands of cubic kilometers, waves tens of meters high, ocean-wide impact, thousands dead, coastal societies disrupted, but not planetary extinction. The Greenland 2023 event is typical of climate-driven failures. Smaller volume, high initial wave due to confinement, SH amplification, limited casualties due to remote location, but the mechanism is now active. Eastern Greenland joins the list of tsunami hazard zones. The pattern will continue. As long as unstable material sits near water, Mega-Tsunamis will occur. Climate change increases the unstable material through glacial retreat. Volcanic activity continues independent of climate. Asteroids remain a low probability, high impact risk. Submarine sediments will continue to fail. The question is preparedness. Can we monitor enough sites? Can we detect events fast enough? Can we warn populations in time? Can we enforce safe building and land use policies? Can we educate people to recognize the danger and respond correctly? These are social and political questions as much as scientific ones. The science is complete. We know how mega-tsunamis form. We can model them accurately, we can measure their impacts, we can predict which sites are vulnerable. What we lack is comprehensive monitoring and rapid response systems, and we lack public awareness. Most people do not know that landslide tsunamis exist. They think tsunami equals earthquake. When a mountain collapses and a wave arrives without ground shaking, people are confused. Confusion kills. Education saves lives. Tell people about Lituya Bay. Tell them about Anak Krakatau. Tell them about Greenland. Tell them that if they live near steep mountains and water, they are at risk. Tell them that if they see a landslide into water, they need to run uphill immediately. Tell them that cruise ships in narrow fjords face real tsunami danger. Tell them the warning time is seconds to minutes. Tell them that survival depends on elevation and quick action. The final lesson is humility. We thought we understood tsunamis. Earthquakes make waves. Subduction zones are dangerous. Pacific Rim has the highest risk. Then Lituya Bay happened. Then Storegga was discovered. Then Anak Krakatau collapsed. Then Greenland rang the planet like a bell for 9 days. Each event reveals something new. Each expands our understanding. The catalog of mechanisms grows. The catalog of vulnerable sites grows. The frequency of events grows. We adapt, we learn, we improve, but we cannot eliminate the danger. Mountains will collapse. Ice will calve. Volcanoes will erupt. Sediments will fail. Asteroids will impact. Mega-tsunamis are part of Earth's natural processes. We can only mitigate, not prevent. And so we return to September 2023. A mountain in Greenland fell into a fjord. The wave sloshed for 9 days. Seismologists around the world picked up the signal. 68 scientists spent a year solving the mystery. They published in Science in September 2024. The paper documents the first mega-tsunami to generate a global seismic signal lasting over a week. It confirms that climate-driven glacier retreat is destabilizing previously stable regions. It proves that confined geometry can trap tsunami energy in persistent seaches. It shows that mega-tsunamis can have impacts far beyond the immediate wave. The seismic signal itself becomes a secondary phenomenon. The discovery changes how we monitor and understand these events. It opens new research directions. It raises new questions. It provides new warnings. The scar on the mountain face remains. The trim line on the opposite shore remains. The damaged research station on Ella Island remains. The sediment cores will show the disturbance. The satellite imagery documents the collapse. The seismic records preserve the 9-day signal. Future scientists will study this event for decades. They will refine models. They will improve predictions. They will learn from what happened. And then another mountain will fall. Another glacier will calve. Another volcano will collapse. Another submarine slope will fail. The cycle continues. The planet does not stop. We ride along. We observe. We measure. We warn. We survive when we can. We learn when we cannot. Mega-tsunamis are not rare. They are not prehistoric. They are happening now. They are caused by mechanisms both ancient and modern. Gravity and instability are timeless. Climate change and glacial retreat are contemporary. The combination is deadly. The geometry determines the impact. The warning time determines the casualties. The response determines the outcome. We know this. We have the data. We have the models. We have the examples. What we need is action. Monitor the vulnerable sites, build the warning systems, educate the populations, enforce the safety regulations, restrict the dangerous tourism, accept the risk honestly, plan for the inevitable. Because the next mega-tsunami is not a question of if, it is only a question of when and where. The mountain face in Dixon Fjord is still unstable, fresh scars, continued rockfall. The USGS warns that the area remains hazardous. Future local tsunamis are expected. This is not over. It is a beginning. The Arctic is entering uncharted waters. Literally and figuratively, what happens in Greenland affects the world. What happens in Alaska spreads globally. The ice is melting, the mountains are falling, the waves are rising. The signal is clear. We can hear it if we listen. 9 days, 90 seconds, one frequency. The planet is speaking. The question is whether we will hear it in time.